Hi, Algebra 2 Honors students. This is Unit 2, Day 7. Today we're going to be taking a look at just a little bit more with transformations. Now, at this point, we've already gone through the transformations graphing calculator activity where you took some parent functions. Here's the list of parent functions I want you to know. And we shifted them in different places. We moved them left, right, up, and down. And we're going to go through some of those recap items today, and then we'll also take a look at some new transformations as well. So in terms of a linear function, we can certainly apply some transformations to the parent function y equals x for something that is of a linear form. When we move over to quadratic, I would want you to know what something of the form y equals x squared looks like. I'm going to challenge yourself that now that we've looked at these on the calculator, we should be able to start taking a step away from the calculator to be able to sketch these. That will be a focus for a quiz that's coming up in this unit. Okay, so for radical x, remember radical x has a starting point at the origin and then goes up and to the right slowly but surely. And finally, absolute value at the very end here for the absolute value of x. That one certainly has a V shape to it. So with that vertex right at the origin. So if we know those parent functions, hopefully based on the graphing calculator lab, you understand how to apply some transformations to these functions. So for example, if I gave you something that we wanted to sketch like y equals, let's do x plus 3 squared minus 2. What I'd want to recognize when I graph y equals x plus 3 squared minus 2 is that it's a transformation of the quadratic parent x squared, right? We have a quantity that's being squared. And what transformations are occurring? The transformations would include translating, which is just a shift. We're going to translate to the whatever's happening on the inside is the horizontal shift. So we're going to translate to the left 3. And then eventually the outside keeps its sign as we move down 2. Okay, so the inside, opposite of what we probably would think should happen. This is going to actually move to the left 3 and then eventually down 2. So if we take a look at that parent function for x squared, we can sort of visualize where that vertex, that minimum coordinate's going to fall. If I go to the left 3 and down 2, doesn't have to be anything too specific just yet. I'll eventually give you some graph paper with grid lines, but the graph might look something like this. To the left 3 and then down 2. All right, so if we're okay with that example, I'm sure we can apply very similar translations, shifting left, right, up, down, to any of the parents above. But what I want to talk about right now is the negative effect. And what I mean by that is the effect that a negative has on a parent function. So I'm going to do this because I think it's sort of nice to view if we're looking at the parent function y equals radical x. So my parent function, I'm going to think about as being y equals radical x. And I know what that looks like, right? If you even want to sketch it in the margin real quick, y equals radical x looks like this. So I want to see what happens when I first of all negate x. So negating x would create the equation y equals the square root of negative x. Well, what I want you to think about is from geometry last year, when you negated the x values for a given function, right? Take all the x values and then negate them. What does that do to the resulting points on that graph? Well, negating the x values winds up causing a reflection, and you're going to reflect over the y-axis. So if I ask you to sketch real quickly for me here, the square root of negative x, this graph right here, you would draw some axes and you would just make the curve go up and to the left instead of up and to the right. So hopefully that makes sense based on what we learned in geometry. Again, negating certain values, negating the x values in this case, flips it over y. So it won't be too much of a surprise that when I negate the y values, that results in a reflection over the x-axis. But I'll tell you, typically we don't write negative y out here because when we graph something, it always says y equals. Almost always, I'll say. So in order to account for negating the y values, where you'll see the negative is actually, in this example, outside of the radical. This is negating the y values because remember, you're going to plug in things for x, take the square root of them, and eventually negate those answers. So these outputs are getting negated, means we're negating y, and that's going to represent a reflection over the x-axis. So can we picture from the parent function what that's going to look like, right? Take this, flip it over the x-axis, negate all those y values. Now it's going to be something that is decreasing. Okay, so compared to the parent, we should be able to now think about if there's a negative somewhere in the equation, let's go ahead and make sure that we do the appropriate reflection. It's either going to reflect over the y-axis or it's going to reflect over the x-axis. So let's see if we can do a combination problem. What I mean by that is let's take a look at something of the form, for example, y equals the negative absolute value of x plus 1 minus 4. Okay, so I want to make a sketch of this, and I also want to list the transformations. And the order that the transformations go in is kind of important. The order I kind of want you to think about PEMDAS. When we think about PEMDAS, parentheses, exponents, and so on, you know, parentheses in this case are the absolute value symbols. So do what's in the parentheses first. Then you would do multiplication next, right? So think about that -1 out front as being a multiplying effect. And then you would add or subtract. Another way to think of this is the acronym HRDV. And H stands for horizontal shift. So if you're going left or right, that definitely goes first. Next is a reflection. After we do reflection, we're going to talk about dilations. We might not do dilations until the next unit, but dilations would come next in the list. And then finally, a vertical shift up or down. Okay. So now that we have that list, I mean, is there a good way to remember it? HRDV? I don't know. I've had other teachers say, Harry really does vacuum. How do I spell vacuum? Is it 2 C's? Well, it's definitely 2 U's. We'll go with this for now. I feel like there's another C. You guys will tell me in class. But anyway, Harry really does vacuum. I'm sure you can come up with something better. We'll see. All right, so now that I have that list, let's see if we can apply it to this given equation. So is there a horizontal shift? Sure is. Step 1, we're going to have to move everything to the left 1 unit. Is there a reflection? Whenever there's a negative, there is. When the negative's on the outside, you're negating the y's, which means reflect over the x-axis. And then finally, the outside is the vertical shifts. We're going to skip dilations for the time being. That will move everything down 4. So if I think about what this graph looks like, we know what absolute value of x looks like as a parent function, right? We know absolute value of x, if I want to sketch the parent, looks something like this. Okay, so I want to take that, I want to move it to the left 1, flip it over, and then eventually down 4. So from the origin, we're going to go left 1, it's going to get flipped over, so now it's going to be upside down V, and then down 1, 2, 3, 4. So the vertex is going to be the point -1, -4, but instead of opening up in that V shape, it's now going to open down. And I realize it's a pretty rough sketch for now, but that's, to be honest, pretty accurate. If we were to confirm this on the calculator, which you can do, we could type that in and see that the graph looks just like this. Now, keeping in mind where we're headed, like I mentioned at the beginning today, is trying to do this without a calculator. Okay. So if we're good with taking something like our parent absolute value and applying maybe multiple transformations, let's consider some other examples where we have some transformations of quadratics. So I want to focus for a little bit on just talking about quadratics. So if I gave you the example y equals x squared plus 4x plus 7. Currently, we would say this is in standard form. So currently, standard form is y equals ax squared plus bx plus c. But we have a goal. If I want to sketch this easily, the goal is to get this into what's called vertex form. And vertex form looks like this, x minus h squared plus k. Because when something's in vertex form, I know where that bottom point is, or I guess that maximum point for that being is. It would be at HK. It would go to the right H and then up K. So the goal is to be able to take something that looks like this and make it look like that, so I know what transformations are happening and what shifts are happening. Well, how do we get there is the question. How do we get there? And the answer is something that is an algebraic process that you've seen before. And it happens to be complete the square. Completing the square is how we're going to get from this form to this form. And I hope that that at least sounds familiar to you. If the process doesn't come back to you right away, we're going to do this example right now. Okay. So as far as steps go for completing the square, the first thing I like to do is I move the C term to the other side. So step 1, move C to the other side. So that's going to become y minus 7 equals x squared plus 4x. Okay. All right, step 2 over here. Take the value b, hopefully you know what b is, right? B would be the coefficient of x. Divide it by 2 and square it. Okay. Now this is a step I don't always write down. I usually do this part in my head, but just for this example, I'm going to write it down. So b divided by 2, that's going to be 4 divided by 2, and then I have to square it. Well, 2 squared is 4. So I did step 2. I took the middle number, divided it by 2, and squared it. What do? Add this number to both sides. Okay, step 3, add that number 4 to both sides. So y minus 7 plus 4 equals x squared plus 4x plus 4. Okay. Now that I've added that number to both sides, what we'll find is that this side is really nicely factorable. Okay. So this breaks down to a perfect square, which makes sense because I'm just completed the square by doing this process. So what I mean by a perfect square is it factors into the same thing twice. Isn't this x plus 2 times another x plus 2? So instead of writing x plus 2, I'm going to write x plus 2 quantity squared. And on the other side, we have negative 7 and 4, which combine to give you a total of y minus 3. And then we're one quick step away. In vertex form, we want y to be alone. So add the 3 to the other side. Y would equal x plus 2 squared, and then plus 3. And this is now in vertex form. So if I asked you, where is the vertex? Where does that turning point occur? The parabola got shifted to the left 2, and then up 3. So the turning point for that parabola is at negative 2, 3. So you might need a little bit more practice just to feel comfortable with this technique. So let's do one more just to make sure we're on the right track here. And then we'll do more practice next time we're together in class. So the last example that we'll do is complete the square for y equals x squared plus 3x minus 6. Okay. Remember the first step from a moment ago? It was add the c value to the other side. So y plus 6 equals x squared plus 3x. By the way, stylistically, other teachers definitely have different ways that they show students to complete the square, but they all get to the same place in the end. So if this doesn't look familiar to you in terms of how you learned how to complete the square, no big deal. But maybe you'll like this way just as much. All right, what do I do? And again, you could do this off to the side if you want. B divided by 2 has to get squared, right? Take the middle term, divide by 2, and square it. All right, well, 3 divided by 2 is not a nice number, and I want you to try to avoid decimals as much as possible because I know how to square 3 halves. It's square the top, square the bottom, 9/4. That's easier for me to determine than it would be if I had 1.5 squared. That might be personal preference, but I bet you'd all agree with me as well. That number is what has to get added to both sides. So we're going to add 9/4 to both sides. Okay. Now that I've added 9/4 to both sides, I remember from before that this becomes some quantity squared. So it's x. I know it's going to have to be x plus something because the middle term is also positive. Okay, if I did this correctly, this becomes a perfect square. Well, the question is, what number here squared would get me 9/4? Oh, wait, didn't I just do that moments ago? This number squared is 9/4. So it turns out that this becomes x plus 3/2 squared. Sometimes writing off to that side is to our benefit, so we can use that information later on. And if you multiply this by itself, you would get a 3/2 x and another 3/2 x. 3/2 and 3/2 is 6/2, better known as 3 for the middle term. So it does all check out there. But I understand fractions can be a little bit sort of tough at first. You'll get used to those. All right, last thing I want you to do is make a common denominator here. So what's 6 as a denominator of 4? Well, if it's 6 over 1, that would become 24/4. If I do that correctly. All right, so now that I have that written as 24/4, if I add that to the 9, we get that this is y plus 33/4. And I know that's not our favorite fraction in the world. That's okay, because we're going to subtract it over and have that in the end in vertex form. The equation here would be y equals x plus 3/2 squared minus 33/4. So to sketch this, I would plot a vertex point at -3/2, comma, -33/4, right? We're going left and then down. And then from there, we have a pretty good idea as to what the rest of the sketch would look like. We would sketch a parabola. So that's a little bit just as far as some more transformations go. It's really nice to be able to get in this transformation looking form. And the way we're going to do that for quadratics is by completing the square. Those are the most algebra intensive as well. All right, that's it for Unit 2, Day 7. Have a great rest of your day.